Hello students, welcome back. Let's resume our discussion in section 4. The last topic, here we go, the uniqueness. Let phi or phi be a real function with n-dimensional vector variables in column vector form with the following properties. Number 1, multilinear. We have n column vectors, and in jth entry, we have a linear combination ax plus by. Then it can be separated, as you can see in the right hand side, and that applies for each column, j equals 1 to j equals to n. So this is basically n linearities put together. It's multilinear. Next, alternating. Switch ith column and jth column, then you have negative of the function value. An immediate consequence of that is if those two column vectors are identical, then even after switching, no change. So no change after taking negative sign, that can be only 0. That's an immediate consequence of this alternating property we saw many times. Finally, the identity property, if we have phi of E1, E2, E3 all the way over to En, then this part forms the identity matrix, and let's suppose phi of that is equal to 1. Then phi has to be the determinant. Now, look at these three properties. Those were the three most basic properties of determinants. Multilinear, alternating, and then the identity property. And we proved all these inductively in theorem 3.5. Basically what we are doing here is the converse. Even if we define a real function arbitrarily, maybe, but if it satisfies these three properties, then it must be the determinant. Now, before proving all this, let's go to section 1 and let's talk about something similar. Actually, the same but easier version. Let phi be a real function with two-dimensional vector variables with the following properties. Bilinear, linear with respect to first and the second variables. Alternating, and the identity property, phi of E1, E2 is equal to 1. Then, this must be determinant, and let's prove it. The proof is not too bad, as you can see. Some algebraic manipulation, and then use of those three properties, and you're going to get what you want. Here we go. Let's begin with phi of A, B, C, D, and our aim is to prove that this is AD minus BC. So how does it go? We can decompose ABCD into two column vectors, AC and BD, blue and red respectively. So far so good. Next, here's some weird step. Let's decompose this column vector into two column vectors, A0 and 0C. And then do the same thing to the right. Why are we doing this? It's a little bit unclear at this moment. Next, factor A and C out, and then get 1, 0 and 0, 1, which will lead to E1 and E2 respectively. Do the same thing in the second component here, second variable. So BE1 and DE2, where E1 is this column vector, E2 is that column vector. Now, it looks okay. Why? Because this is a linear combination, and that too is a linear combination. Now I can see why in the world we did this and that. I wanted to get this linear combination. That's why we did it. Once we have this linear combination, we can use property number 1, multilinearity, and we can decompose with respect to the first variable, and that's what we have over here. AE1 plus CE2 form. leaving the others exactly the way they used to be. Now, the first term can be decomposed with respect to the second linear combination in B E1 plus D E2. How about the second term here? We can decompose with respect to the second term, like B E1 D E2. Okay, alright. We're done applying multilinearity. Now let's look at the other properties. Do you recognize that E1 and E2, E2, E1? Oh, alternating, so switch those two and get E1, E2, and that'll give me negative sign. Alright, how about the others? Well, E1, E1, two identical columns, so that is 0. E2, E2, two identical columns, so that is 0. And then what about E1, E2? That gives me identity matrix, so value is 1. Same goes over here, E1, E2, so that value is 1. So we have 1 and 1. And here's the conclusion. AD minus BC. Yes, indeed, this is a determinant. So the conclusion. If you have these three properties, multilinear, alternating, and identity properties for 2D version, then it is a determinant in 2D. Now let's go back to the original problem here. Why did you go back and do this 2D? I have two reasons. Number one, I wanted some warming up. Something easy first, and then go to a more difficult one. Number two, we're going to be using mathematical induction. So we need a base case, and we just did the base case. Base case was n equals to 2. We did it. And then we're going to apply the mathematical induction with the inductive hypothesis. When we have n minus 1 order, then it's okay. We have this uniqueness. And then we're going to prove it for n. Ready? Let's go. Base case done. All right. First decomposition. Okay, all right. We have this n by n matrix, and we have all these columns. First column, second column, third column, and then dot, dot, dot. Now, let's decompose the first column into A11, bunch of zeros, and 0, and then bunch of non-zeros. This is kind of analogous to what we did for this proof here. At step 1, we did this decomposition, A0 and 0C. Do you remember? And do that for n-dimensional case, and this is what we get. A11 and bunch of zeros, and then 0 and then bunch of non-zeros. Factor A11 out using multilinearity, and we have 1 and bunch of zeros. And then we have 0 and bunch of non-zeros. This is the first decomposition. Here, let's look at the first term a little bit more carefully. And let's simplify this further. And here we go. This first term is reproduced over here, all right? A11 was there before. Now, let's decompose the second column. A12 and bunch of zeros, and 0 and bunch of non-zeros. And then factor A12 out, as before, and we have 1 and bunch of zeros, and here 0 and bunch of non-zeros. Look at this matrix here. First column and second column are the same. So phi of this is going to be 0 by the alternating property. So that one drops out. And then I have only this part. So we have 1 and bunch of zeros, and 0 and bunch of non-zeros. Did it get better? Yes, this 0 is important. Let's work out the third variable here, third column vector here. Decompose A13 and bunch of zeros, and 0 and bunch of non-zeros. Same thing. And then we do the same thing here. Factor A13 out. And what we have? We have 1 and bunch of zeros. We did the same thing now 3 times. And then here we have 0 and then bunch of non-zeros. Now 1 and bunch of zeros, and then 1 and all these zeros. These two are identical. So phi of this is 0. So this entire part drops out. By alternating property, this is 0. So we only have this part. So what did you get so far? 1 and all zeros, and 0 here, non-zero, 0 here and non-zero, and then we still need further work here. But I hope you see the pattern. Repeat this for the 4th column, 5th column, 6th column, all the way to the nth column, and we can kill off all this first row and get all these zeros here. Conclusion. We get first 1 here, all these zeros, and all these zeros in first row. So let us abbreviate it like this. 1 and bunch of zeros here, and bunch of zeros vertically, and we have deleted matrix A11. Please note that this is a deleted matrix A11. So let's abbreviate like this. And then if I go back to the original decomposition, this became that. So we can write like this. A11 times this expression times phi of this. Phi of this. That's the final expression. Not the final expression. That's the final it's not a final expression. There are many more things to do. Excuse me. Okay, anyway, this is what we got. A11 and phi of 1 and bunch of 0, and please take a look at this A11. We want determinant, right? We want to prove that phi of A is determinant. And for that purpose, we need A11 and the deleted matrix, and indeed we have it here. As a matter of fact, I'm kind of skipping a step, but this is actually a determinant. And you see, the first column is fixed, 1 and all 0, so no variable here. And first row is fixed, 1 and all 0 there, so no variable there. So all the variables that can change belong here. So let us rename it into another function by introducing another character. Let's use next Greek letter C of A11, because everything that is important is over here. Then this is a n-1 variable real function with n-1 column vectors of dimension n-1. Basically, this is n-1 by n-1. And then what's the property? Multilinear, alternating, and the identity property. We have them all. So this is actually the determinant of A11 by the inductive hypothesis. By the inductive hypothesis, this is a determinant. Whenever you have multilinear, alternating, and the identity property, then it's a determinant up to n-1, and that's the inductive hypothesis, and we are now proving for n. So this actually is a determinant. So what we got over here is basically determinant of A11 we got here. Now if we work this out further, and then determinants of A12, and then determinants of A13, and so forth, then we're going to get a complete answer here. Okay, let's work this out. Let's go to the second decomposition. Let's work out this. And we do something similar here. We decompose the second column, A12 and bunch of zeros, and 0 and bunch of non-zeros. Same thing we have done before. And factor A12 out, we have 1 and bunch of zeros, and 0 of bunch of non-zeros. Next, we switch the order of these two columns so that this falls in the first column, 1, 0, 0, etc. And this falls in the second column. And by alternating property, we need the negative sign. I don't have to do anything here. Now, let's simplify this one and let's see if we can get rid of all these zeros here. And indeed, yes, that's what we are going to do. Let's look at the third term and decompose it at A13 and bunch of zeros, and 0 and bunch of non-zeros. Same thing again, and take this A13 out, and 1 and all those zeros. It comes out, which is the same as the first column. So by the alternating property, this entire thing drops out. That's 0, and I have only this part. And what did you get? 1, 0, and then 0, and then we have some more work to do here. But if you repeat it, I'm going to get another 0, 0, 0, and we are going to get all zeros. So, repeating all that, we get this expression, 1 bunch of zeros, and then here, everything that is important is all here. Deleted matrix A12. Do you see that? Red column is out, so this is A12. So what we have, A11 phi of this, A12 phi of that, but as I showed you before, you can reduce this into a multilinear alternating function with identity property for n-1 dimension, so it's a determinant. And likewise, this 2 is a determinant. So as a matter of fact, we got up to here. This is determinant of A11, and this is determinant of 1, 2. We got up to here. And then we got 0 and 0, and we have to start with the third one. See the picture? Move this to the first column by 2 alternation. So we have minus and then another minus, so we have plus. And then do exactly the same thing as before. You have to get that. And then we have 0, 0, 0, and then now we have some non-zero starting here. And exactly the same thing. The fourth column, we can move it to the first column by taking this 3 alternation. 1, 2, 3, and then go all the way to the top. So we have -1 to the third power, we have negative, and do exactly the same thing. So we have this. And all these are determinants. And go ahead, and what do you get? All these are determinants. And we have determinants of everything. So we have determinant, oh yes, indeed. If you want really precise explanation, they're all here. With all these phis, and then introduce C, and use the inductive hypothesis to conclude these are all the determinants of the deleted matrices. Consequently, we get these in place of phis of all those, and consequently, we are getting the determinant of A. Difficult proof? Oh yes, indeed. Both theoretically and also technically. But here we go, we completed it.